So when we add and subtract derivatives, we can do the derivatives separately. The next question is, what happens if we're multiplying? What happens if we wanted to take the derivative of x sine x? Or 3x times e to the x? How do we do that? So Leibniz said, well, if adding and subtracting was so straightforward, why can't multiplying be so straightforward? Everything that we've done with derivatives so far has been beautiful. It looks nice. Derivative of sine is cos. Like, it's just, wow. So why can't, if I have two functions multiplied together, why can't I just make them derivative of each and work from there? Well, if we look at a simple example, we'll find out that this isn't going to work. So we've got y equals x, and g of x equals x to the 4. Okay? If you multiplied those together, you would get x to the 5. And x to the 5 is an easy derivative. It should be 5x to the 4 using our power rule. So when we times x to the 4th, we know the derivative should be 5x to the 4. But if we kept them separate, and we did the derivative of just x, and did the derivative of just x to the 4, we would get 1 and 4x cubed. And then if we multiplied those two together, we get 4x cubed. And it doesn't match up with the 5x to the 4. So Leibniz's first guess was wrong. She's like, well, maybe I'll go with my second guess. This one. I'll just take the first function and multiply by the derivative of the second function. Then I'll add the second function multiplied by the derivative of the first one, and it should work out. And it does. Okay, this is on your formula sheet, because this is the first complicated function. But the idea is this. So I'm going to use some different colors, highlighting again. I'll say that again. We've got our function f of x. It's multiplied by our function g of x. Our one function stays the same, and then we multiply it by the derivative of the other function. Then our other function stays the same, and we multiply it by the derivative of the other one. Since we're adding, the order here doesn't matter. You just need to take the derivative of one of them and keep the other one the same. Derivative of the other one, and then keep the other one the same. Okay? In the other notation, instead of f of x times g of x, we've got one function u and another function v. Again, we keep one function the same, and then dv dx is the derivative of the other function. And then keep the other function the same, and du dx is the derivative of the first function. So both of these are on our formula sheets. And so here are first of a couple questions. You can do all three of these ones. Well, yeah. So with the product rule, if you're going to use the product rule, you have to recognize where is the multiplication. Okay? Right here are two things that are multiplying. Maybe you want to label the first one as f of x and the second one as g of x. Or maybe you want to label the first one as u and the second one as v, depending on which of those two formulas you feel more comfortable looking at. So if we're looking at the first formula, it says keep the first one the same and then multiply by the derivative of the second one. And the second one's 2x minus 1. The derivative will just be 2. Plus, now keep the second one the same. What's the derivative of x squared? 2x. Simplifying this, we're going to get 2x squared plus 4x squared minus 2x. Combine our like terms. And we get y prime equals 6x squared minus 2x. Now I mentioned once you get your answer and you've simplified it, look at your function and ask yourself, is there another way that I could do this? This question could have been asked before we learned the product rule. Because what could I do with my original function? I could have multiplied it out right at the beginning. And if I multiplied it out right at the beginning, I would get 2x cubed minus x squared. And then it's a simple power rule 1. The 3 comes out in front. And in this case, that little simplification at the beginning is probably easier and more straightforward than using our new product rule. Okay? Look at the next two. The next two as well, you can find out that yes, I could simplify these. Both this one, I could simplify that one first, and you just use my power rule. Same thing with this one. I could multiply that out, expand it completely. It's a little bit more involved because it's a binomial times a binomial, but not too bad. And that may be easier than using the product rule. But the nice thing about these two examples, example 2 and 3, is you can use the product rule, simplify it, and then you have another way to check, is it the right answer? But with the ones in example 4, that option isn't there. You can't multiply these together nicely and then get new functions that are easy to do. See how you did on this first one. See, the multiplication is right there between those two functions. So we think of the 3x plus 1 as our first function, and the natural log of x as our second function. Keep the first one the same. Derivative of the second one be 1 over x, plus keep the second one the same. Derivative of the first one is just 3. And you can leave your answer like this. It says we do not need to simplify our answer. Leave it in brackets. Don't even need to multiply that 3 times the natural log of x and put the 3 in front. This is fine just like this. There's part B. Try part C as well. Check your answer for part B. And then check your answer for part C. So using the product rule right away. Then multiplying things out. Combine your like terms. We get our answer. Or if we multiply it out to begin with. So multiply the 2x through everything. You get 2x to the 5 plus 6x to the 4 plus 12x. Then multiply the negative 1 through everything. And combine all of our like terms at this point. Whoa, did I mix? I mixed up. Here we go. 6x cubed minus 3x cubed. It's 12x minus 6. Yeah. Perfect. So multiplied everything, combine our like terms. Now, taking the derivative, 10x to the 4 plus 20x cubed minus 9x squared plus 12. And it's exactly the same. Looking at each of them as a comparison. They both took 3 lines to get to our final answer. I'm not sure if one was necessarily less algebra than the other one. The second one, I would say taking the derivative was easier. The first one, I would say the multiplication was easier. So you'd have to decide which one you like better. Two more examples, and then if we have time, we'll make up a crazy product rule one, just for fun. So with the product rule, the biggest skill you have to start to get is recognizing when there's two functions multiplied together. And the way to do that is to look for x, right? Here I've got 2x, that makes that a function. Then I've got sine x, that makes it a second function. So in doing our derivative here, we're going to have to use the product rule. Then that is, the derivative again, is all of our tangent lines at every single point. So if we want to find the slope of the graph at x equals pi, all we have to do is plug in pi. Think of our unit circle values. Cos of pi is -1. Sine of pi is 0. So we get a slope of -2 pi. Too quick, should I go back? Good. So this last example, we're going to find the slope of the normal. Well, how are we going to do that? Well, we'll find the slope of the tangent first, then do the negative reciprocal. So again, do you notice that the equation has two functions multiplied together? Keep the first one the same, derivative of the second, plus keep the second one the same, derivative of the first. A strategy that's going to come up a lot that's really helpful algebraically, is there something in common? Because if there's something in common, we can factor it out. There's an e to the x that's in common in both of them. So we can factor that e to the x out, and then you're just left with negative sine x plus cos x inside. So then if you want to find what's the slope of the tangent, you can plug in pi. Sine of pi is 0. Cos of pi is -1. And then multiply that by that e to the pi. And then you've got your slope is negative e to the pi. Negative reciprocal would be 1 over e to the pi. have 3 minutes left, which is enough time to have a little bit of fun. So, what happens if our original function was 3x squared times e to the x times tan x? What's the difference in this question from the ones we've done so far? We have 3 functions multiplied together. So how do we do 3 functions multiplied together? Well, we think of them as 2 functions multiplied together, where one of them has 2 functions inside of it multiplied together. So our product rule said one function times another function. So we need to pick a point on here somewhere. Maybe I'll pick the first multiplication, and I'll think of it as 3x squared times the second one. Okay? So I'll go through our product rule. Our product rule says keep the first one the same. All right, things are going good so far. Multiply that by the derivative of the second one. So the second one is the one that I have in brackets, in the red brackets. Well, how do I do the derivative of the second one? The derivative of the second one is a product rule. So now I'm just going to do the derivative of the second one, which means I have to keep the first one the same multiplied by the derivative of the second one, plus keep the second one the same and multiplied by the derivative of the first one, and the derivative of e to the x is e to the x. Whew. Now, what have we done? We've just done the first part of our product rule here. We still need to go plus. Now keep the second one the same. And I'm just using the brackets here to help you visualize what's happened. We kept the second one the same, and now we're going to do the derivative of the first one, which is just 6x. Now that you've seen that with 3 functions, you could do one with 4 functions. And you could do one with 15 functions if you wanted to. And the answers just get longer and longer and longer. But if you didn't have to simplify it, you could just leave it like that, and it would be done.